Hey everyone, this is going to be a very rough talk about this paper, Fast Algorithms for Convolutional Neural Networks. It was published in CVPR 2016, and then I'm just going to give quite a lengthy introduction and the intuition behind this paper. So let's start. So a shameless plug before we start this talk. If you're a DNN researcher, how do you make sure that you're using the fastest neural network package? Well, go to this benchmark in GitHub, and it lists all the possible different libraries and how fast their forward and backwards passes are. Most of the state of the art as of today is going to be close to cuDNN release 4, release 5, which incorporates these Winograd-based FFTs. So make sure to have these backends installed if you want to take advantage of the fastest convolution in the world. So what is this paper about? It's about reducing the number of floating point operations when computing a convolution. The definition is actually a bad one. It's actually when computing a set of convolutions, not just a single convolution. So we're going to demonstrate what this means with the Winograd FFT algorithm. And the motivation of this paper is we always want faster convolutions for applications like pedestrian detection, so we don't hit people with our cars, or object detection on a mobile device, which is resource constrained, power constrained, and what have you. Yeah, cool. So the first thing that we're going to talk about is the convolution theorem and why it matters in this context. And the idea behind the convolution theorem is we've been doing convolution in the time domain, which is considered a dot product. But in the frequency domain, we don't do dot products, we do pointwise multiplications. So the difference would be less multiplies, the number of multiplies is equivalent to the number of inputs, and no adds. It's just straight pointwise multiply in the frequency domain. How this looks like is in this theorem. You can go on Wikipedia and search for this formula under convolution theorem. And the idea here is we have two inputs, f and g. F is our input in the case of deep learning convolutions. G is the weights, and the idea here is we're going to take G, take its FFT, take F, take its FFT, and then perform a pointwise multiplication. Once we compute that pointwise multiplication, we just take the inverse FFT, and that's indeed equivalent to what's called the cross correlation between F and G. So just real quick to talk about cross correlation and convolution. From what I understand, cross correlation and convolution are very similar. The difference from what I've been reading is the order of the kernel G. So, oh man, what happened? The order of the kernel G. Basically, cross correlation does not flip the kernel. In the DSP sense of convolution, it flips the kernel. So just watch out for the true definitions of convolution and cross correlation. In deep learning, we're doing cross correlation. So to make this more concrete, let's do an example. So let's say our input is the following 1x4 vector. Our filter or weights is going to be this 1x3 vector as well. And the idea to get the convolution in the traditional time domain, we would basically superimpose, not superimpose, sorry. We would take the first 3-element window, stick our filter on top, and do pointwise multiplication, the dot product between the two. So it's going to be 10 times 0 is 0, plus 20 times 0 is 0, plus 30 times 1 is 30. So the first element is going to be 30, which is indeed 30. Likewise, if we do the second window, so this is going to be a second window, we're going to slide the filter 10, 20, 30 we're going to do a similar dot product. 20 times 1 is 20, plus 30 times 2 is 60, 20 plus 60 is 80, and that is indeed the convolution output for this guy. So that what I just demonstrated is the time domain version of convolution. It looks like the operations that we've done is basically this direct or dot product approach. If you count the number of operations, there's going to be 1, 2, 3, 4, 5, 6 multiplications. There's 1, 2, 3, 4 additions. And just so you call out my arithmetic, I did verify this in NumPy using the cross correlation function between f and g, and indeed gives us 30 and 80 as the output. That's great. So that's the dot product approach. That's what we've been doing when we do the direct method or the regular convolutional way. The convolution theorem approach, the FFT or the transform-based approach, we're going to do something very similar. So F0 is our first sliding window. F1 is our second sliding window. G is just our filter right here. GG is the inverted filter. So we need this because this method, you have to be careful about the order at which you present your filter. If you want to do cross correlation, you have to flip the filter in this case. Yeah, we have to flip the filter. So here's the steps where we take the FFT of, in this first step, we're going to take the FFT of F0 right here, which is just the first convolutional window. FFT the filter. So the output of this expression right here is going to be a 1/3 vector. We take the inverse FFT of this guy, the 1/3 vector, to get the same dimensional 1/3 vector, another output vector of size 1/3, which is shown here. And you'll notice that we have extra outputs. All we care about is this last output right here, so we can discard this. There's this theorem called, or there's this method called this overlap and save. And the idea is we're overlapping the inputs, and then we're just discarding several outputs and keeping one output right there. Similarly, for the next output, we convolve the second sliding window for the input with the filter, do the IFFT, and you get the actual result right there. So, and we just discard those two outputs. So that's good. That's great. That's awesome. The convolution theorem approach definitely works. It's sound and it's functionally correct. Let's now count the number of operations. So I'm listing right here a symbolic, the computation symbolically. So let's count. There's 1, 2, 3, 4, 5, 6 multiplications. So that's true about the pointwise multiplications. But what about the operations to do the FFT and IFFT? Doesn't that include overhead? So what gives? Where is the savings from the dot product approach to the convolution theorem approach? And it turns out that this is actually, just for correctness, there's faster ways of computing the convolution theorem, which we'll go to on the next slide. So this guy in the 50s, Samuel Schmel, Winograd, invented a way to compute this convolution approach to the FFT very quickly. So this is a very specialized algorithm, and the idea here is his function takes two inputs. The first is the number. The parameter 2 represents the number of outputs. So if we look at the output matrix, there is indeed 2 output elements. So the first one is the number of outputs. The second parameter is the filter size. So if you look at the filter matrix right here, there is indeed three filters, 3 elements in this filter, a 3 by 1 vector. So what's implicitly encoded in this formulation is the number of inputs, and the number of inputs is a m plus m plus k. Is it k? It's r. M plus r minus 1 input value, where m is the first parameter, that's m, and the second parameter is r. So in this case, 2 plus 3 minus 1 is going to equal 4. This is the size of our input. And if you look at the input matrix, let me erase this for a second. If you look at the input matrix, right here, there is indeed 1, 2, 3, 4 unique elements in the input matrix. The reason why it's laid out like this is it's laid out in how we would traditionally look at the convolution. So look at the review the previous example, and you'll see that this sub-expression is just the first convolutional window, and this next expression, this next row, is just the next window in the sliding window input. So the formulation is sound, and the idea here is let's formulate our inputs and weights as a matrix vector product. The traditional time domain way of doing it would be to dot product these matrices, compute the matrix product to get a 2-element output. But instead of doing that, we're going to do basically a very special formulation. Basically, we're going to calculate the outputs based on a sum of products. So these are the sums, these are the products right here. And if for more information, you can go read the fast algorithms for convolutional neural networks paper by Andrew Lavin and Scott Gray. But the basic idea is, in this formulation, if we count the operations, there is, let's start with the data. Let's start with this guy. There's 1, 2, 3, 4 adds from the input. So these are our data or Ds. On the filter side, we have 3 adds. So this is this guy. That's one add right there. That's another add right there. This is considered another add. This is the same sub-expression, so we don't actually have to add anything. G0 and G2 can be added in one step, so that's how we get 3 adds. The 2 multiplications happen when we multiply by 1/2, and that's how we get 3 adds and 2 multiplies for this kernel. The outputs now, we're going to do 4 multiplications. So the outputs are the m's. So to get the outputs, we do we take the product of this expression. So this is one expression multiplied by that expression. This is the first expression multiplied by that expression. We're going to do 4 of those expression multiplies. The last 4 adds comes from combining the m's to generate the output. So one thing to notice in the context of deep learning is these are basically free because you can pre-compute this right before you start your network. So all of their G's can be folded into a simplified sub-expression away from the critical path of execution. But you'll definitely have at least 4 multiplies and 8 adds in this case. So it's definitely reduced the number of multiplications by a factor of 2.25. So this is the number of multiplications for our dot product approach, and the bottom number is the number of multiplications for the Winograd approach. So that gives us a savings factor of 2.25. 2.25 doesn't seem too much in this example, but we'll learn that it actually makes a big difference when we create two-dimensional convolutions. When we nest these expressions to create two-dimensional convolutions. So just real quick, the paper posits the following. You have n plus r inputs, and the number of multiplications. This micro symbol is basically what's the minimum number of multiplications that we need to compute the this function, and it turns out it's the number of inputs is related to the number of multiplications you're going to be doing is related to the number of inputs. So if you have m plus r inputs, you will have m plus r minus 1 outputs. So that's nifty. That basically says we have we can bound the minimum number of multiplications. In this, we're almost close to the end. I wanted to end with how this applies to 2D convolutions for deep learning. And basically, I'm just going to be hand waving in this section, but the idea is we have original function f, the Winograd convolution method, and we can actually nest it into 2 dimensions. And the number of multiplications here is equivalent to this guy right here, m plus r minus 1 plus m plus r minus 1. What's really, so right here. So if the input size is 2 by 2 for m, and r is 3 by 3, the number of multiplications is m by m, which is 16. That's cool. I like that. This is the arithmetic complexity. Oh, I think 6 over 4 is not 2.25. It's like 1.5, I think. Sorry. I don't know how to do arithmetic. Okay, and I guess I wanted to end with the following formulation, just so you guys can see how this translates to deep learning. So let's say we have a formulation such as the following: f of 2 by 2, comma 3 by 3. So we know from this formulation we're going to deal with 3 by 3 filters. So here's an example of a 3 by 3 filters, and the first parameter m by m means we're going to generate a 2 by 2 output. So implicitly the input's going to be of size 4 by 4, and when I mean input size, I mean a single input tile. So let's say this is our input. It's a 7 by 7 input. I zero padded it because it makes this demonstration much easier. So what this formulation means is the following. I'm going to break up my input into 4 by 4 tiles. And within these 4 by 4 tiles, I'm going to do a series of 3 by 3 convolutions. So that's my first convolution. That's my second convolution. And remember, when I mean by convolution, I'm taking the dot product. You can visualize it as saying I'm convolving this green window with this filter, and how you do the convolution can either be in the time domain way or the frequency domain way. This works well in the frequency domain way. So let's continue. This is the third convolutional window, and then the last convolutional window is the purple box. So basically, this formulation works on input tiles of 4 by 4, and every time we generate we process a single iteration of this function, we're processing 4 outputs at a time. So in the context for this convolution for my contrived example, after this function is executed, it will output the four convolutional values that we would have done in our original example. And then this is one set of four. We would then shift this window over until we consume the whole input. So go over that example if it's unclear, but that's the basic gist of what this function does and how it maps into this matrix. So we save multiplications by a factor of 2.25, so what, who cares? And it turns out that Facebook did FFTs a while ago, FFT-based convolutions a while ago, and I'm just going to touch base on a couple of results on their 2013-2014 paper. So this paper was the second paper from Facebook that came out. And basically, what's graphed here is, for a particular problem size, I think the problem size is the size of your input, so n by n. This heat map basically shows you the speed up relative to what I think is the direct method of doing convolutions. And we want values that are green because it means we're closer to 16x than a 1 over 16x speed up. So this is bad, this is great. And what you'll notice is each facet in this graph varies the kernel size. But the performance only rocks as we increase the size of the kernel size. For the longest time, 3x3 and 5x5 kernels couldn't, with this technique, we weren't able to actualize a good speed up. We used to be in this big kernel regime. What the fast algorithms for deep convolutional networks paper does is enables us to do 3x3 or smaller filter size kernels. So which is arguably what's common in today's deep neural networks, 3x3 filters. So this is a graph from their 2013 paper, and basically this is a 7x7. There's this trade-off. The red line is the FFT-based method. The blue line is the direct method. For 3x3, this graph looks very different. I suspect it's going to be closer to this. Oh, whoops, that's not the right color. Red is the FFT, and then blue is the direct method. Basically, for the 3x3 filters, this gap is too low. We want this gap to be as high as possible, as high, for instance, right there. And you can validate that. I think this is my suspicion. I basically opened a spreadsheet and tracked the number of operations, full input operations, and this seems to be the trend that's happening for 3x3 filters. So basically, in short, before this CVPR paper, 2016 CVPR paper by Andrew Lavin, 3x3 filters, it was not economical to compute 3x3 filters. Some last parting words before we end this presentation. That's cool about the convolution theorem. So this paragraph says that this is basically cheap. The inverse transform is cheap and can be amortized over channels. So that's awesome. I was concerned that the overhead of doing the FFT and IFFT would be too great. This says that so the problem with FFTs is it operates on complex valued elements. So a single pointwise multiplication actually decomposes into 4 real valued multiplications. But thanks to this sweet property called the Hermitian